got sunlight coming in. We already talked about the fact that you've got some energy in. So this is sunlight. And then when it heats up, you reach thermal equilibrium, and that just means that the energy going out of it is equal to the energy going in. Energy absorbed or energy in is equal to energy out. And at that point, power absorbed is equal to power out when it's in thermal equilibrium. So the big picture of this packet, I know sometimes you read and you get lost in like the steps and you lose sight of what they're doing. In the first part of it, first several pages up to I think equation 8 derives this term. The next several equations derive this term. And then they take this term and set it equal to this term, and they solve for what they want. And what is sort of, why are we doing all of this? What value do we want to get, ultimately? What value are we going to use our spreadsheets to tell us?
What we need to make the oven?
Yeah, like
we need to get the outputs we want.
To get the output, and specifically which output are we most interested in?
Temperature?
Yeah,
temperature of the interior of the oven. So that's what they set these two things equal to each other, then they solve for temperature of the interior of the oven. And it's equal to, basically, it's equal to the ambient temperature. So that's just the normal air. If you took your oven outside and just put it there, if it was just a cardboard box, eventually they'd be equal. But we're going to add these terms. And it's pretty simple once you understand it. There's a term on the top which represents basically the energy in, and there's a term on the bottom which basically represents energy or power out. And the bigger the numerator is versus the denominator makes this a big number, and so we add. I mean, that's conceptually what that equation is. So let's just clarify for ourselves one more time what the main pieces of these are, and eventually, and I was actually going to give it to you today, but I decided that would even be cruel for me. But I was going to give you a little quiz, and that quiz was pretty simple. The first question was, without any notes, write down this equation. Because if you understand this equation, you can write it down. Just like I might not remember Newton's second law, but acceleration is directly proportional to net force and inversely proportional to mass. I understand it. That is a little more complicated, but if you really understand, like, that's pretty simple. If you understand this term and this term, these are pretty simple too, but that would be too cool to just pop that on you without announcement. The other question on the quiz would look something like this. It would have a list of variables. For instance, I sub 0 and theta plus maybe sine of theta plus beta, maybe area of the window, maybe that little tau, maybe the absorption coefficient. And in this column, I would ask for the units. In this column, brief description. And in this column, do we want it big or little? Like, are we trying, is a big one of these? There's another, there's U also. Is a big U good or is a big U bad? Is a big A good? Is a big A bad? Et cetera, et cetera. So, is anybody ready right now to take this quiz? If you are, we can just do that.
Wait, for sine, will we describe theta or B as being big or little?
So, this whole term. And so let's pick one. So for instance, let's pick transparency. What would be the units of the transparency coefficient?
Oh man, that was
that one in joules.
Okay, well, let's talk about this first. So we've got a certain amount of power coming in, and on a day like today, well, okay, let's start from the beginning. Let's start with this one. And we'll get to this. So this, what conceptually does this represent?
The temperature on the inside where the food is.
That's not the temperature. That's an eye.
This is I.
That's an eye. That's so
Just the
Okay, let's start with this one.
area of the window.
Area of the window. Now, do we want, or what are the units of area of the window going to be in?
centimeters and meters. Meters cubed.
Squared. So probably in some metric systems, so they're probably going to be meters squared. And on your spreadsheet, you need to be really careful. Mr. Enrique, I'm sure, will tell you, like, you need to know what your units are, and the units all need to work together. Because you might pick up a value off of the internet, oh, the thermal conductivity of this thing is blah, blah, blah per centimeter, blah, blah. But if you just convert everything to centimeters and degrees Celsius, you'll be fine. So meters squared. And a brief description, what does this represent?
Just the
window.
how big the window is.
So the area of the window. So blah, 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 area of window. Now, in general, do we want this as big as practically possible or as tiny as practically possible?
Big as possible.
Okay, so we want it big because this is what's letting in our energy, and we need energy in there to cook our food. All right, so let's say I have a big window. Let's say the area of the window, in this case, let's say it's 0.5 meters squared, so half a square meter. That probably none of yours are going to be that big, but it's an easy number to work with. How are we going to know how much energy hits it?
Well, should we see what PVC types we have in
So the IO.
That would be this. This represents the intensity of the sunlight.
That's what it was. Intensity I.
So I represents intensity. So let's think about what would be the units of intensity. Okay.
Watts per. Water per meter second.
Does it make sense why it's per meter squared?
Yeah.
If it's just watts, like what does that mean? How much is coming out of the sun?
Watts.
How much is that hitting the earth? So we want to know like watts per meter squared. So on a day like today, it's probably around 800. Whoa. 800 watts per meter squared. And it's probably at least, it's probably right around there. We could go online right now and look it up right at this minute. It'll take 2 minutes to do that, but it's very easy to do. Okay, so that's how much energy is. Well, let's go through the process. So the units are watts per meter squared. What would be a brief description of that?
The solar intensity that hits your window.
Okay, that's true, but you can't define something. You can't give a definition of something and use that same term. So I want a brief definition of solar intensity.
How much energy? How much solar energy is?
Okay. Is there a difference between energy and power?
Yes.
So let's use the right one because this is using watts. So the power, full sentence.
The power that's hitting the ground,
window.
No, the window. The amount of power from the sun that's hitting the window.
Okay, that's really close. In general, it's the amount. This variable represents the power of sunlight hitting any square meter of Earth. I mean, if you happen to put your window in there. This 800 doesn't represent how much is hitting your window. It would be half of that actually. So it's just a variable that represents the intensity of the sunlight and tells you how much power hits a square meter of surface area. But you're on the right track. Now, in general, do we want that big or small?
Big.
We want that big. Okay, good. Let's go to this one now, the sign of this, and that had to do with orienting it toward the sun. What are the units of that?
Degrees.
Like, is it an angle?
Radians?
I know.
Uh-oh.
Well, if you're taking the sine
Would it be meters as well?
It's sort of a trick question.
Oh.
There aren't any?
There aren't any. It's a
That's
unitless
easy.
number. It's a unitless number. The sine of 45 degrees is 0.7 whatever. There are no units on that. It's a unitless number. It's just a number.
None.
So none. Brief description. What does this represent?
The angle.
The angle that the sun's rays makes with the ground and
Not with the ground.
Not the
but
ground,
where
like
the angle of the oven.
yeah.
the angle of the oven.
Yeah, it sort of has to do with the
That heated
alignment
amount.
of the sun's rays to the oven.
The
And
oven to the
what's the biggest the sine of anything could be? One. What's the smallest?
0.
So on that scale, do we want it big or little?
the middle.
I want it to be little, so it would just be like directly looking at the sun.
No, one means it's looking directly at the sun.
Yeah, if it's
One
one is,
means
like, directly
it's
looking
directly
at
at
the
the sun. So you want this as big as it could possibly be. It just
Two.
turns out that as big as this could be is one. So
So the-
as big as possible. Big. One. You know what I just did there when
Yeah.
I tilted that? I made that one by making no shadow on this. I make that one. Okay, so now we've got this term. We're really close.
Transparency.
Now we have tau. The percent of it's the percentage of how much comes through the cat like the first time.
Of how much does it seem like?
Light comes into the window.
Yeah.
Something like it does.
And then the end is just how
The
many
percent
windows.
of.
So we've got this term, power absorbed, and we're saying it's the area of the window times intensity of the sun times this sine of theta plus beta, which is just going to be 1 and isn't going to. We just talked about, what else? Or is that all we've talked about so far?
Yeah.
So that's how much energy is hitting our window. Does all that energy go through the window?
No.
No. So only maybe 90-something% of it goes in. That's the tau.
It's 98%.
98%. So that's the tau. Let's just look at the product of this. What would be the units of the product of this?
Would be
What are the units of area of the window?
meters. So we
What are the units of
watts per meter squared.
watts per meter squared?
So it would just be watts.
What units do we want power to be in?
Joules. Whoops.
Or joules.
I thought energy was in joules.
What's the unit of power?
Oh.
Watts.
That's what I said. Watt is the unit of power.
Watts.
WATTS.
That's what I said.
Stop.
He's on WATT.
So, this is unitless. What are the units of tau going to be?
Is it also unitless?
What's that?
Is it also unitless?
It's also unitless. It's a coefficient. Coefficients don't have units. It just tells you what fractional decimal amount gets through there. So if I multiply watts, let's say this was, we had our, 0.5 meters squared times 800 watts per meter squared. I have 400 watts hitting the top of this. 0.98% go through, unless I have dual pane. In that case, it's another tau. But I don't need to do that. I could just say tau to the number of windows that I have. And that's unitless. So that tells us how much sunlight gets through the window. But what I really want to know is how much is absorbed. Out of all of the light that hits here, do we think 100% of the light hitting here is going to get sucked in and absorbed?
No.
No. If it's white, less than half of it is. If it's as dark as possible, a flat black paint, then 90-something% of it. So we've got another coefficient which represents the absorption of the interior box of your oven. And that's, Andrew, what is that called? What variable do we use for that, do you think, to represent the absorption? It's A. So A is just one more coefficient, and it's going to be 0.90-something too, because most of the energy is going to be absorbed if you've got a dark surface. A small amount will then just reflect off and go back through your window. But this together, these two have units and these are all unitless. This represents the power absorbed by your oven. So now let's open our packets and compare this to equation 8. See if we can see any similarities between this and equation 8.
Equation 8 has this sign.
Yeah, that's there.
Yeah,
It's the same.
Yeah, that's
Oh,
it.
well, that's
Same
okay.
thing.
it's the same thing.
This is equation 8.
Wait
Yeah.
a minute.
Basically, it's
So the next section is on
leading.
so now we have the power absorbed, then we just need
The power
the
out.
power out, and then you just set them together and you do a very simple algebra to get equation 14. So let's just talk a little bit about power out and what sorts of things would affect power out. So we don't have to worry about the power coming in. All we have to know now is that it's hot inside and it's cooler outside. And so heat goes from hot to cold, energy goes from hot to cold. What variables are going to affect how much energy leaves every second, aka power out? What circumstances or variables of the environment or of the oven are going to affect this?
Robot.
The insulation. So talk about that. What's the insulation going to do?
It's gonna basically keep the hot in and the cold out.
Okay, so heat does not travel well through insulation. It's going to sort of be a blanket. It's going to block energy from going out. Energy's still going to go out, but it's going to slow it way down. So we have a variable. We've got a few variables, and you'll read about it. One is called R, which is sort of like how well something insulates. It's called R. We have another one called U, which is the thermal conductivity.
Aren't those just inverse?
Yes and no. They are in the sum. If you have the net R or the net U, they're inverses of each other, but you'll read about it. You can't add them up. They're a little different. But you can also think about them as being inverses of each other. But this is the one that ends up in our equation. So this just describes how well something conducts heat. So by the way, would we want this big or small, U?
Thermal conductivity.
You want it small because you don't want it to be a good conductor.
In the packet it says U is the overall heat transfer coefficient in watts per meter squared times degrees.
So we'll get to that in just a second. So
But I thought it was unitless.
first of all, you thought what? I'm sorry.
But then you said it's the coefficient, so it's unitless.
Did I say it's a coefficient? This is a variable. This is a mechanical
Oh,
property.
They didn't call
It
you a
says-
coefficient.
Those other ones. This is
Coefficient.
these are coefficients. This is going to have units. Okay. So this is a variable, a property of anyhow. Let's just move on. We want this small because we don't want it to conduct well. So what other things, besides what type of material, because you just sort of describes what type of material, what other things are going to affect heat coming in and out?
The double pane.
Okay, so we also have double or single or triple. We also have heat coming out here, and it turns out that there's a U for the sides and bottom, assuming that you're insulating the box the same. And you don't have to. You could break it down into U of the sides and U of the bottom, but it might just be easier to have one type of material all the way around. And you've also got a U for the window, which becomes a little bit of a problem, as we'll find later on when we get to that. So what else besides thermal conductivity?
How cool it is outside.
And how would that affect anything?
So if it's like, let's say
If it's colder outside, what would that?
you're not gonna get as much energy into your solar oven.
We're not talking about energy into the oven right now. We already had that discussion. That discussion ended with this equation. We are strictly talking about how much energy is going out of our oven.
More energy will go out of the oven
If,
if it's cooler outside.
why?
Because the heat will transfer from the oven to the outside.
What's going to happen anyways? Why would a colder,
Because
it's already doing that.
It would be harder to reach equilibrium, or the
Yeah,
equilibrium
it's a more
would be
drastic difference.
lower.
Yeah.
It's a more drastic difference. The bigger, it's not necessarily the temperature outside or the temperature inside, it's the difference between the inside and the outside. The greater that difference is, the more energy you're going to get flowing. I mean, you know this already. If I've got a potato that's 90 degrees and it's, or let's say 100 degrees, and your body temperature is 90 whatever, 8.6, if you grab that potato, not much energy is going to go from that potato into your hand. It'll feel a little warm, but not that much energy is going to flow into your hand. If this is 800-degree potato and you grab it, now there's a big difference between the temperature of the potato and the temperature of your hand, and you're going to
faster.
That hand's gonna.
yeah, so the amount of energy that flows through something is partially dependent on the material, partially dependent on the change of temperature between here and here, and there's one more variable that you probably know, and it has something to do with the physical design of this thing.
Area.
How thick the insulation would be.
Oh yeah,
How
the
thick the
thickness.
insulation is. So the amount of energy flowing has to do with the temperature difference, the material, the thermal conductivity of the material, and how far it has to go. The further it has to go, the more it has to fight through there, and it's more insulation is the better. So now we answer your question: what are the units of U, Ian?
Watts per meter squared times degree Celsius.
Those are words.
No, sorry. Watts per meter squared, and is
It's right there.
on the bottom
And then C.
per degrees Celsius. Now let's see if that makes sense. So let's open our packets now. What page are you on?
9.
Well, well, isn't temperature measured as Celsius? In this one? So then wouldn't that cancel out? Wouldn't that cancel out with temperature? So then it would be left with meters per watts. That for overall heat transfer coefficient.
But what would cancel it out?
Temperature. Because temperature's in
Oh,
Celsius.
you're saying like the whole equation.
Oh.
T is at the
Yeah,
top and
it's
then
gonna.
C at the
Yeah,
bottom.
all of it's gonna
T in-
cancel out to being watts still.
We just have to find some heat molecules and put them in there. No, Ian, you idiot. They traveled out
So what
the
page
air.
are you on there,
Cooled by
Ian?
the cold molecules.
Page 9.
Okay, so, well, there's the equation number 9 right there. P is equal to U A delta T. So the amount of power through something, in this case out, but through something, is equal to directly proportional to the heat transfer coefficient, directly proportional
The area.
to the area.
What's the heat flow?
We didn't talk about that, actually. And then
The temperature.
delta T.
Yeah.
So if we're talking about how much energy is going through a wall, it's not just the thickness of the wall. The thickness of the wall is actually gonna affect U. That's where the R factors come in or not. The more area we have, the more surface area we have, the more energy is going to come through. Does that make sense? If I've got a 1 square inch window you know, or a piece of metal and it's hot on one side than the other, so much energy is going to go through there. If I've got 1,000 times more of the surface area, I'm going to get 1,000 times more energy. So it's directly proportional to this. So if we look at this, the watts, this is going to be watts per meter squared per degree Celsius, because this is going to be meters squared and this is going to be degrees Celsius, and we need this, so all these things to multiply out to just be equal to watts, because that's what we're trying to get. So you're going to have to read a little bit about U. I don't want to talk about that right now because you can ask me questions. But basically, they derive P in, they derive P out, they set them equal to each other, and they solve for T interior of the oven. Now there's one problem that's going to occur, so go ahead and look at the equation. I think it's equation 14.
It has like both of them. I don't understand both.
The internal is based off of
Okay. So, and equation 14 is not that, if you look at it now, it sort of makes, hopefully makes some sense, but you should look at how they actually derive that. The top part of that fraction is basically the power in, and the bottom one is very much related to the power out.
What does it mean by SB?
Sides and bottom. USB is sides and bottom, UW is window. So we've got this equation.
So basically this equation is just finding the surface temperature.
But then ambience here. Equation 11 is multiplied by temperature.
We've got this equation, T interior of the oven is equal to T ambient plus basically power in USB area plus U window area of the window, area of the sides and bottom. Now here's the problem. They talk about this hidden problem. If I had all of these things, if I had all of the things necessary to calculate these, I'd be good. The problem though is
You need the overall heat.
the
You need the U.
UW of the window is dependent on what? It's dependent on this, and this is dependent on this. There's a little bit of a problem here. You can't solve this because you don't know this until you know this, but you don't know this until you know this. So whenever you have two variables, unknowns, in one equation, you're screwed. What else do you need? You need another what?
You need another variable.
Oh, the temperature.
No, then you'd be really screwed. You've got two variables in one equation.
Oh, you take one of them out, so you only have one to solve for.
But then how are you going to solve that one if you need the other one?
By one another.
Yeah.
If you have two variables, what do you need?
Make a graph.
You need two of something else. We have two variables in one equation. If I told you x is equal to y plus 3, can you tell me what x or y is?
Oh, you need another
Oh, the system of equations. Oh.
I need some other. 2x is equal to 1/2 y minus 7. Can I do this?
Yeah.
Yeah, absolutely.
Negative.
Well, first of all, let's talk about what are some ways to do this. What would be one way to do this?
Well, multiply one of them, y's or x, to like make it cancel each other out.
So
elimination.
I could do elimination. I can multiply across by 2, then add them, blah, blah, blah. What's another way I can do it?
Substitution.
I can just take this and plug it into there, solve for y, and then plug that back into either one of them. What's another way I could do it? What's the easiest way?
Graphing it.
If I graph them,
And then the intersection point.
the intersection. So that's sort of where we're at. Now, the cool thing is, in this reading on page, if we go back
So you get a type.
to page 10, and you look at that table, that's a very useful table. So look at that table and see see if somebody can explain to me in their own words what that table is about. What's that table telling us?
The temperature, like, of the time of day, like the different times?
Nope. Has nothing to do with times.
It's saying like whatever your temperature, your initial temperature in the interior is, that's gonna depend on what your UW is. So it's kind of giving, like if this is 66.
Now, the temperature of the interior oven is going to depend on a lot of things. You said it backwards. Try it again, just switching.
So whatever UW is gonna give you what the initial.
No, you now use the word depend.
Oh, UW is gonna depend on your initial or your temperature inside the oven.
So because the interior of your oven, your window is right there. Whatever that interior temperature oven is going to affect UW. So UW is dependent on the interior oven temperature. So they give you a table, and they give you a table for 1 or 2 windows. And if you made a graph of, well, we could do it either way, of temperature of the interior oven versus UW, it doesn't matter how you graph it. I forget exactly, it's gonna be some sort of a quadratic. They give you enough data in there, they give you some data points, and with these data points, you could actually get the quadratic model. You could put into Logger Pro or Desmos or whatever, put in the data that they give you, figure out the relationship between these two. It's going to be quadratic. You could try other models and they sort of get you close too. But now you've got 2 equations and 2 unknowns, because these are the 2 variables in equation 14. So the easiest way to do this would be then just create a graph. Graph equation 14, TIO versus UW, whatever. Graph this equation, and the intersection is going to be the interior temperature. Now there's other ways too. You can algebraically solve this. I did it 1 year. It took like 6 pages of paper, and then I could never do it again. So either I deluded myself and I made a mistake, or I just got worse at algebra. But I'm pretty sure I did it 1 year. So you could do that. You could also use Excel. There's a goal seek function. So Mr. Enrique could help you with that, but you can like run lots of UWs until you get to like this that you want. There's a way to use goal seek, but the easiest way to do it is just graphically. Goal seek will give you a little more exact example. On this one, you just sort of have to zoom in on this and sort of estimate it, but it's all an approximation anyways. So that will get you within a few degrees of the prediction. So try your best to understand the model first. Once you've understood it, then start marching through those Excel spreadsheet instructions.
Ow.
Okay. To be honest, if it takes another day or 2, like if you're not done by next Friday, it's not the end of the world, but it's just the longer it takes to do this, the less building time we have, so we don't want to take forever. But do your best to understand the theory first. Don't just jump into the spreadsheet, because then it's just sort of meaningless. If you understand these variables that you're working with, have a little bit of an intuition for them, and their units will help you too. Take some time and do that, and then once you're feeling confident, a little bit comfortable with that, maybe some of you are now, then just go for the Excel spreadsheet. Help each other and talk to Mr. Enrique.
We make it our own, right? Or
What's that?
We make it our own? Or do we
Yeah,
share?
everybody's going to make their own spreadsheet, but you're going to want to work together to figure it out. Okay, cool. I'm done. You can have that, Michael.
Nice.
Finally,